For this slide, I will explain the problem overview of cellular satellite communication. Cellular communication is commonly used in our daily life for mobile phones, internet access, and data transmission. However, cellular communication depends on ground based towers to provide coverage. The problem is in certain areas such as remote villages, mountains, oceans, and disaster zones, cellular coverage may become weak or totally unavailable. This can happen because there are not enough towers or the existing towers may be damaged during disasters. So, to overcome this issue, satellite communication can be used because satellite provide wider coverage from space. This allows communication to continue in areas where normal cellular towers cannot reach. However, satellite communication also has some limitations. It may have high delay, signal loss, weather interference, expensive equipment, and lower data speed compared to cellular network. Therefore, the main problem is how to maintain stable and reliable communication when cellular signal is weak or unavailable. A combined cellular satellite communication system can help solve this problem by switching from cellular network to satellite network when needed. This system is important because it can support emergency communication, rural internet access, maritime communication, aviation, remote operation, and disaster recovery. That is the problem overview for this project.
My name is Chin Jingwen, and I will be presenting analysis findings. We need to understand why connectivity remains a challenge in rural areas despite our advancements in cellular technology. First, the causes. As we analyze, rural deployment faces a triple constraint, which are geographical barriers, economic unfeasibility, and infrastructure gaps. Unlike urban environments, rural areas are characterized by challenging terrain, mountains, dense foliage, and valleys, which cause significant signal attenuation and disrupt line of sight. Next, due to low population density, mobile network operators face a very low return on investment, making the capex required for fiber backcell towers hard to justify. Then, many remote regions lack stable power grids, forcing reliance on expensive, logistically difficult off-grid power sources. We then evaluate the technologies currently in use. Traditionally, this includes low-band 4G LTE and GEO satellites. However, our technical analysis identified two major failure points. First, terrestrial limitations. Using the Okumura-Hata model, our simulation showed that signal power drops below the critical negative 110 dBm threshold after roughly 12 kilometers in rural terrain. This creates massive coverage dead zones that isolated rural tower cannot fix alone. Next, latency constraints. While geosatellites provide wide coverage, they operate at an extreme altitude of nearly 36,000 kilometers. As shown in our latency simulation, this results in a round-trip time of over 270 milliseconds, which makes real-time applications like telehealth or video conferencing virtually impossible. To summarize, to summarize our analysis, the current ecosystem operates in silos. Terrestrial networks are limited by distance, and traditional satellite networks are limited by latency. This technical deadlock is the primary reason why rural areas remain disconnected.
Proposed solution to address the rural connectivity problem, we propose an integrated CDMA, which is code division multiple access based spectrum system combined with LEO satellites. As studied in my syllabus, which is chapter 5, CDMA is a hybrid of FDMA and TDMA, which is frequency division multiple access and time division multiple access that uses spread spectrum technology. In our system, each rural users is assigned a unique PN code that is orthogonal to other users' codes. All users transmit simultaneously over the same frequency band without requiring time synchronization. At the receiver side, the original signal is recovered through correlation with an synchronized copy of a spreading code. The system consists of four main components: user terminals with DS-CDMA capability, LEO satellites acting as repeaters, a gateway Earth station that spreads signals and connects to the terrestrial network, and the network core managing routing, authentication, and billing. CDMA, which is Code Division Multiple Access, offers four critical advantages for rural areas. First, fading channels. In rural areas with vegetation and terrain variation, CDMA shares signal degradation among all the users rather than crippling a single user like FDMA world. Secondly, flexibility. No precise time coordination is required, which is ideal for remote users with varying propagation delays. Third, privacy. PN codes provides inherent security critical for emergency and agricultural data. Fourth, jam resistance. Frequency hopping over a wide bandwidth resists interference and natural noise. Now, looking at our key calculations, the processing gain is 398 or 26 decibels, which allows weak signals to be detected even below the noise floor. Using the CDMA capacity formula, our system can support approximately 477.6 or 478 users per satellite beam. Additionally, the bandwidth efficiency is 3.46 bits per second per hertz, calculated using Shannon theorem with an assumed bandwidth of 200 kHz and signal to noise ratio of 10 decibels. The expected improvements include coverage increasing from 30% to 95% or more, latency reducing from over 600 milliseconds to just 30 to 50 milliseconds, enabling real-time communication, user capacity increasing from 0 to 477.6 or 478 user per beams as I mentioned before, and signal robustness becoming reliable even in multipath environment.
Good day. My name is Divya Kumari Anapapa Rajakumar and my metric number CN230132. Today I'm going to talk about technologies evaluation. So for this slide, there are challenges, technical description and engineering implication and also impact on integrated network. So the first slide outlines the foundational physical and resource challenges we face when integrating the LEO constellation and terrestrial networks. First, the sheer capital expenditure required to launch a satellite and upgrade ground gateways with complex tracking antennas significantly increases the financial risk and inevitable drives up consumer costs. Beyond these financial barriers, we are constrained by infinite physical resources such as overlapping 5G and satellite frequency bands, risk severe interference that requires advanced cognitive radio solution to mitigate, while the strict power budget for the solar reliance satellites combined with the high energy demands of the ground stations ultimately bottleneck our edge computing capabilities and conflict the global green telecom initiatives. So for the next slide, I'm gonna continue by talking about cybersecurity threats and also regulatory and compliance issues. So we shift our focus from physical constraint to the operational and geopolitical risk of managing these integrated networks. Cybersecurity is a primary concern because Bridging terrestrial IP networks with space asset expands the attack surface. So, for a single vulnerability to jamming, spoofing, or unauthorized access could compromise data and services across massive geographic regions. Furthermore, we face significant legal friction because satellite footprints naturally ignore national border, forcing operators to navigate a complex, often conflicting web of local telecom laws, international spectrum and allocations, and also the data privacy mandates and space debris regulation of all, can severely delay our global deployment. Thank you.
In conclusion, next generation cellular technologies are transforming rural connectivity by overcoming challenges such as limited infrastructure, high deployment costs, and difficult terrain. Innovations like satellite integration, Open RAN, AI-driven network management, and renewable energy solutions enable reliable and sustainable communication in remote areas. However, achieving universal rural connectivity requires collaboration between governments, telecom providers, and local communities. By working together, we can ensure that everyone, regardless of location, has equal access to the opportunities of the digital world.